we still have them h apart, this volume that I have is simply A times h, and the electric field is constant, and so I get here that this is 1/2 epsilon 0. For E, if I want to, I can write sigma divided by epsilon 0. I can square that, and dv, in doing the integral over all space, means simply I get A times h. It is the volume of that box, so I get A times h. And so this is now the total energy that I have. I lose one epsilon here. I have an epsilon 0 squared, and I have an epsilon. I also remember that the charge Q on the plate is A times sigma, and that the potential difference V, this now is not volume, it's the potential difference between the plates, is the electric field times h. The electric field is constant. If I go from one plate to the other, the integral E dot dl in going from one plate to the other gives me the potential difference. And so I can substitute that now in here. I can take for A sigma, I can put in the Q, and you can also show that this is 1/2 QV. V being now the potential difference between the plates. And so this is a rather fast way that you can calculate what the total energy is in the field, or to say the same thing, the total work you have to do to assemble these charges, or to say it differently, the total work you have to do to create electric fields. You have created electric fields that were not there before. I now will introduce something that we haven't had before, and that is the word capacitance. I will define the capacitance of an object to be the charge of that object divided by the potential of that object. And so the unit is coulombs per volt. This V is volt now, it's potential. But we never say that it is coulomb per volt in physics. We write for that a capital F, which is farad. We call that 1 farad is the unit of capacitance, undoubtedly called after the great maestro Faraday. We will learn more about Faraday later in this course. So let us go to a sphere which has a radius r, and let us calculate what the capacitance is of this sphere. Think of it as being a conductor, and we bring a certain charge Q on this conductor. It will then get a potential V, which we know is Q divided by 4 pi epsilon 0 r. We've seen it many times. And so, by definition, the capacitance now is Q divided by the potential, and therefore this becomes 4 pi epsilon 0 r. So that is the capacitance of a single sphere. And so we can now look at the values as a function of r. I have here some numbers. I calculated it for the Van de Graaff, and I calculated it for the Earth. If you want 1 farad capacitance, that's a real biggie. You need a radius of 9 times 10 to the 9 meters. That's the 4 pi epsilon 0 that comes in there. That's huge. That's 25 times the distance from the Earth to the Moon. That's a big sphere. We have a capacitance of 1 farad. The Earth itself, with a radius of 6,400 kilometers, would have 700 microfarad. The Van de Graaff 30 centimeters radius would be 30 picofarad. The pico is 10 to the minus 12. And if you take a sphere with a radius of 1 centimeter, then you have roughly 1 picofarad, 10 to the minus 12 farad. So this gives you a rough idea about the size of objects and how they connect to their capacitance. So if I bring all these spheres at the same potential, so I charge them all up to the same potential, then the one with the largest capacitance will have the most charge. And that, of course, is where the word capacitance comes from. It is the capability of holding charge for a given electric potential. Don't confuse that with electric fields, because if you bring all these spheres at the same potential, then the one with the strongest electric field, that's the one which has the smallest radius. We discussed that last time. Now, I will look at the situation a little bit differently, I have here a sphere, B, positively charged, and I place it close to another sphere, A, which is negatively charged. And so, by my definition, I can say that the capacitance of B is the charge that I have on B divided by the potential of B. That would be my definition. But there is here this object which charges negative. And how did we define potential? Potential was work per unit charge. I go to infinity, I put plus Q in my pocket, I approach B, and the work I have to do per unit charge is the potential of B. That's the definition of potential. But B is repelling me, so I have to do positive work. But A is now attracting me. And so the work I have to do is less the work per unit charge. And so, because of the presence of A, the potential of B goes down, and therefore the capacitance of B goes up. And so now you see that the presence of this charged sphere here has an influence, an important impact on the capacitance of B, and therefore it is really unfair to call this the capacitance of B. We think of it as the capacitance of B in the presence of A. So it's no longer just B alone. And so I'm now going to change the definition of capacitance. And I'm going to change it in the following way. I have two conductors. And these two conductors have the same charge but different polarities. And now the capacitance of this combination of two conductors is the charge on one of them, which is the same, of course, on the charge of the other, except different polarity, divided by the potential difference. So that now is my new definition of capacitance. So you always deal with two objects, not with one in isolation. If you have the charge on one of the two, and you divide it by the potential difference between the two. You may say, well, it's a little artificial to have two conductors, and one is positively charged, and the other has exactly the same amount of negatively charged. Well, it is not so artificial as you may think. Remember then we had this Wimhurst machine, which I was cranking, and I was charging one plate positive and the other one negative. And without my doing anything, if one becomes positive, the other one becomes negative by exactly the same amount, because you cannot create charge out of nothing. So if you charge one thing positive, chances are that something else is charged negative by the same amount, but with opposite polarity. So it's not